Hello, everyone. My name is Smita Raut, and today's topic is going to be clustered file system as container persistent storage with applied security. So here's the agenda. We are going to go through the introduction and set some baseline with the concepts that are going to be used ahead in the presentation. Then we'll be talking about some data sharing use cases for distributed or clustered file systems. Then we'll look at how to secure that shared data and what kind of security aspects can be applied onto the storage for this kind of use cases. And we will conclude with a short demo and illustration. So let's start with the introduction and set the baseline. Now to talk about containers, why containers? Now, if we look at our traditional monolithic applications, they typically scale by size. They replicate monolithically. Each component has to be replicated in order for the entire application to work. It changes monolithically. Any change to one of the component affects the integration of rest of the components. As opposed to the microservices architecture, in which it scales by microservice replication, it is easier to deploy changes. It is easier to manage changes because only that component which you are changing gets affected without affecting the entire integration. So with the advancements in monolithic or with the advancements in microservices architecture, its adoption is also increasing. And some of the areas where it is widely adopted are multi-cloud, wherein it can be an on-premises or a public cloud. Now, why they are being very popular in multi-cloud kind of use cases is because of elasticity in the scheduling and its auto-scaling nature. It provides the benefits of improved resource utilization. They provide secure isolation, multi-tenancy. Some other advantages are portability and reproducible serviceability. They are also easy to deploy. For example, one-click laptop to supercomputer deployment is also possible. Another use case of containers is in development, DevOps, and continuous integration. Because it is easy to make changes, it is easy to develop in this kind of an environment. We can take advantage of reuse of applications and services, and it just accelerates your deployment and application deployment. So for faster development, faster deployment, it is widely being used in DevOps kind of an environment. And also containers are being used in microservices architecture, as we just talked about, because of programming language agnosticity and also independence from the technology stack that it is being deployed onto. Again, a common advantage for containers is faster and easier deployments. So these are just to name a few, but containers bring in a variety of use cases and plethora of applications for which they are being widely adopted these days. We have seen evolvement of Docker container runtimes. There are newer runtimes coming in, and as the workloads are increasing, it is becoming increasingly important to manage the containers and manage more of containers. So with that respect, excuse me. With that respect, Kubernetes becomes one of the de factos. It is by far one of the most popular open source container orchestration platform and is used for managing a cluster for containers management. So in subsequent slides, I'm going to be using Kubernetes as an example in many of the charts. Now next, let's look at what is a cluster file system. Now, cluster file system, or call it parallel file system or distributed file system, Although there might be some differences in these terminologies, but at the heart of it, the similarity is that they are mounted on multiple servers or multiple nodes, and multiple nodes are accessing the same data. So that is the distributed nature of this file system, which brings out, the accessibility of the same data from multiple access points. Some of the examples of this kind of file system are IBM's Spectrum Scale file system. We have Luster, Gluster, Ceph, even NFS is a distributed file system. So what we are going to see next is the container persistent storage. We have seen how containers are important, and Kubernetes is an important orchestrator engine for managing container clusters. And we have also seen what are distributed file systems. Now, just to take a look at what the container persistent storage is and how Kubernetes particularly manages its volumes and its persistent storage. So if you look at the left-hand side diagram, this is how it typically works in Kubernetes. The developer typically claims for a persistent volume from a pool of persistent volumes by using something called as PVC, a persistent volume claim. Now, once that claim picks up a persistent volume, it binds to that volume and gives it back to the developer. The developer can then use this volume to mount it inside any of their application pods. Pods is a single scheduling unit of Kubernetes in which your applications run. So a developer associates that PVC to a pod, and pod in turn exploits the data inside the PVC, which essentially is your storage data. Whatever storage backend you have, the storage is provided by that. So this is the Kubernetes typical volume management. Now, there is a specification called Container Storage Interface. Again, it is an open source specification being worked upon by various communities, and the main intention for this interface was to provide a unified interface for any kind of storage and for any kind of container orchestrator system such as Kubernetes. So the typical architecture of this storage is you have something called as sidecar containers, which are external provisioner and external attacher that are deployed onto your Kubernetes server. And they kind of intercept the requests coming from kubelet for creating the volumes, deleting the volumes, or attaching the volumes to the application pods. These requests are then intercepted by the external provisioner and external attacher, and they are passed on to the volume drivers. So if you can see, the external attacher will pass on the request to the volume driver, which in turn contacts your storage subsystem and provisions the storage for Kubernetes and creates PVCs. At the same time, you see these other nodes, these are particularly worker nodes. They also have kubelet deployed, which is used for servicing the data and providing it to servicing the IO basically. These are used for IO paths, and kubelet then talks to the local volume driver for servicing the IO. So this is how the pods perform the IO onto the PVCs that are provisioned onto your storage subsystem. And this is the, at a very high level, architecture of container storage interface. So this is just to set some baseline and introduction to the Kubernetes volume management world and container storage interface, which we will then exploit subsequently in various use cases for data sharing that we are going to look at. So let's look at some of the data sharing use cases. One of the very basic use case of any distributed file system is read-write many, or RWX as it is termed in Kubernetes terminology. So when you create a PVC, you can define the access mode for that PVC, whether it is read-only, whether it is read-write once, or whether it is read-write many, which means there is an external storage out of which a PVC is provisioned, and multiple pods can write and read to the same storage through that PVC. So you can see there is a pod associated or running on this worker node, which is accessing the external storage, and there is another pod running on this worker node, which is accessing the same storage. So we have two pods accessing the same storage, and this is the use case for read-write many. But what will happen if both these pods are accessing the same storage with different users? So that is also an aspect to be considered. Pods can run as different users as well. Next use case that I want to talk about is the multi-cluster use case. In the earlier one, we saw that different pods from the same cluster are accessing the same storage. Here we have different Kubernetes cluster, the left-hand side Kubernetes cluster, and then we have the right-hand side Kubernetes cluster, both trying to access the same storage, and which is a very legitimate use case, especially in case of distributed file systems. Again, in this case, there can be different users trying to access through the pods and trying to access the same storage. So this is multiple Kubernetes cluster who can read write to the same storage. Then we have multi-protocol access. We have already seen that how a pod that is being used to access access storage via PVC using one of the users, say user 1. Now, it is also possible your external storage can have other applications. It can service, let's say, NFS or SMB or HDFS. It can service other kinds of workloads also. So in that case, your external storage is being accessed by some storage server and is being also exploited by another user using any of the other protocols. It is also possible, this is also a very much possible use case in case of a distributed file systems, where Kubernetes pods and native clients are reading, writing to the same storage. And then we have the multi-cloud use case, wherein you can have an on-prem setup of Kubernetes and pods from the on-prem setup are accessing the external storage. But you want to replicate that storage, or you want to replicate that entire setup onto your public cloud or some other private cloud. So you have cloud 1, you have cloud 2, both trying to access the same kind of storage because they want to run similar applications. This kind of a setup, or this is a very good use case if you want to migrate your applications from one cloud to the other, from on-prem to a public cloud or on-prem to your private cloud. So, but if your applications are moving, it is also essential that they find the data they need onto your cloud. For that, you also need some mechanism to do a storage sync. Now, I'd like to give an example of IBM Spectrum Scale, which caters to this kind of use case by one of its enterprise class features called AFM, Active File Management, which is an asynchronous replication, or you can say it's an asynchronous replication, and more than just replication. You can sync the data from one site to the other, and you can manage the storage that way. Uh, so that is just an example. You can use any other replication mechanism to kind of make your storage available onto the cloud. At the same time, you would also need your PVC configuration to be available onto the public cloud. So for that, some kind of Kubernetes metadata sync is also needed. And this way, you'll be able to access the same storage with the same security characteristics from various clouds. Now we have seen these data sharing use cases, and let us also see how to secure your data that is being shared. So let's first talk about Kubernetes security. When we talk about Kubernetes security, we are talking about the security of the entire stack. For any application that is cloud native, there are typically 4 layers of security, which are called 4 Cs in the cloud native security: cloud, cluster, container, and code. By cloud, what we mean is the entire cloud provider security, or the storage provider, or your data center security. So these are some recommendations provided by cloud provider or your storage providers. Then comes the next layer, which is the Kubernetes cluster. So Kubernetes has its own security constructs, and it involves securing the various cluster components and applications of Kubernetes. Then comes your container security, which involves containers, typically involves the securing of your images, like image scanning, signing and enforcement, etc. And then the application that is deployed onto your container, which is the code level of security. So these are the 4 Cs of cloud native security. Now let's look at one level deeper into what Kubernetes provides as part of its security standards. One of which is pod security standard. So Kubernetes defines how one can secure its pods by means of namespace isolation, by using pod security policies, whether your pods can be privileged, whether they have restricted access to the resources on host, what all operations or what user your pod can run as, whether it's a privileged user or a non-privileged user. So all these things can be defined as part of your pod security standards. Then there are network policies for pods, whether you want to isolate your pod in some network or whether you want to run pods as non-isolated. Then there is cluster level security, providing access control for the Kubernetes API or the kubelets by means of service accounts or roles and cluster role bindings, etc. It also provides runtime control for workloads and user capabilities. And then we also have data encryption. Data encryption in transit for control plane can be configured, and data encryption at rest for various secrets that are configured for Kubernetes resources. Now let's look at the storage level security aspects as well. And since we are talking about distributed file system, we'll talk about distributed file system level security. Typically, it would be files or directories or some kind of grouping of files. So we had seen earlier how the PVC is bound to one of the PVs from the pool of persistent volumes. And persistent volumes are typically mapped to the storage volumes that your storage subsystem provides. So this entire thing, PVs to the storage volume binding, is managed by the CSI driver. And all storage subsystems have to write their own CSI drivers. So for example, in case of a distributed file system, your volumes can map to files or a group of files or directories, whatever is defined by the storage subsystem. So one volume is a one logical unit that will map to a PV. Now, in these volumes can be controlled by volume ownership. So files, for example, can be owned by a particular user. So it is natural that that particular user will have access to the volume. Then for more fine-grained granularity of access control, you can provide ACLs. ACLs will tell you what operations the user or the owner can perform, or the users inside a particular group can perform, and what operations others can perform. So this is your typical chmod kind of an access control, where you give read, write, and executable access. These are given in terms of three bits, 777 bits. But you can also have extended access control. So in addition to user group and other, you can define what other users can access this particular volume and in what capacity. So you can define masked entries, and you can define what other users can access, whether they can read to this volume or write to this volume, etc. So this is an example of POSIX ACLs, but similarly, you can also, if your storage subsystem supports, you can also use NFS ACLs, and it depends on what ACLs your storage subsystem supports. But typically what we are talking about is volume ownership and ACLs on your volumes. So this is your storage level security. Now, let's look at SELinux. SELinux is also an important aspect when you're talking about securing your systems. It is a security feature by Linux kernel, and it defines how the processes can interact with other server components, how the processes can access the resources on the server, etc. So typically, a process will perform the request onto the resource, which is called action request. Let's say it's a read request. So if your system is SELinux, your system is working in SELinux enforced mode, then this kind of a request will go to the security server, the SELinux security server, which is configured using various SELinux policies. These policies define what kind of rules are there for this particular process. The policy is basically a rule definition that defines what to give access and what not to give access. So the policy server or the security server will check the policy and define if the permission for that particular kind of access should be granted to this particular process. If the permission is granted, then the access is granted to the process. Otherwise, denied access log entry is logged and to varlog messages, which you can monitor and audit. So in the world of containers, SELinux also plays an important role. Docker can be configured to run with SELinux enabled by using one of the flags. OpenShift heavily uses SELinux. It uses cryo runtime, and it uses SELinux in enforcing mode. And also OpenShift uses volume SELinux relabelings heavily. So when the pods mount a volume, it also, for extra security, it also relabels the volumes so that you can guard who else can access the same volume. Sharing of content between the containers is handled by relabeling options, whether it's -z or -Z. Based on that, you can define who can share the contents of this particular container. Now let's look at the pod level security. We saw the storage level security, we saw the kernel level security, and now let's look at the pod level security that will come into picture when we are bringing all this together. So in a pod, you can define a security context. It can be defined on a pod or on a container as well. So in a security context, you can define what user this pod can run as. So there is a construct called as run as user and as group that defines what user or group this pod should run as. There is also something called as FS group, which is the supplemental group. So in addition to run as user and run as group, you can give access to a supplemental group also. In the pod security context, you can also define your SELinux security context. You can define what are the levels of SELinux that this pod should be using as. Then there is another aspect as well for pod security, which is called pod security policy, or in OpenShift terms, it is called security context constraints. That centrally enforces security policy on pods across the cluster. You can associate a PSP or an SCC with your pod. This PSP also includes UID, GID, SELinux, privilege escalation settings that we have seen. In SELinux settings, you can define whether the SELinux setting is must run as, or it can run as any kind of a user. Now, with these security constructs, I would just like to give a brief illustration on how it all works together. So let's say we create a PVC1, with the owner John, whose UID is 1000. And then you want to deploy this, or you want to mount this PVC inside a pod. So this PVC is mounted inside pod 1, which is being run as user John. So when John tries to access the data from this PVC from pod 1, he will be granted access. Now let's say there is a pod 2, which is being run as user Jane with UID as 2000. And when Jane tries to access the data on PVC, she gets access denied. Now, let's say we add an ACL to this particular PVC and grant access to Jane. In that case, when Jane tries to access the pod or access the PVC, she will get the access. Now these owner, ACL, UID, these settings can be managed by your CSI driver. And let's look at how the SELinux will take into account. So as I earlier mentioned, OpenShift is one distribution engine for, or is a distribution of Kubernetes that heavily uses SELinux, and it mounts or relabels the volumes when the volumes are mounted inside the pod. So from pod 1, John will be able to access the PVC, but at the same time, OpenShift will relabel the PVC and assign some SELinux labels on it. Now let's see what happens if another pod is spawned again by the same user John, and it's trying to access the same PVC. But it will get access denied because even though it is being used, even though the same user John is trying to use the PVC, it is getting access denied because now the volume is relabeled and your pod is not using those labels to kind of access the volume. So what you can do in this case is you can define security context for SELinux options and define the level which should be using while accessing the PVC. If with this change, you will be able to access the PVC, And at the same time, you have to consider that all the pods that should be using this particular PVC need to run with that particular level. So these are some of the examples of security measures that you can take in case of data sharing use cases. All these use cases that we have seen are read-write many use cases where multiple pods are trying to access the same PVC, multiple users are trying to access the same PVC. With this, the conclusions that I draw are that clustered file systems or distributed file systems, although they open up many new possibilities and use cases for effective data sharing, their security and access control is very vital. Especially in this kind of data sharing use cases, it is very important to understand that since there are multiple users trying to access the same data, there can be malicious users also, and hence it is important and vital to protect your data. Uh, Kubernetes does provide strong security constructs, like we have seen the pod security constructs and some other cluster security constructs to guard the shared data. And also, CSI helps in leveraging storage subsystem security features in this kind of an overall use case. In the end, I would like to talk about IBM Spectrum Scale and how it enables these kind of data sharing use cases with utmost security. Spectrum Scale is highly scalable, high performance, unified storage for files, objects, along with integrated analytics. It provides POSIX HDFS interface as well as NFS SMB interface along with object interface as well. And now it has a CSI driver to enable workloads in containers as well. It enables global collaboration with its unified storage, providing a global namespace. And it is very effective in data lake serving like HDFS files and object across multiple sites. Um, in terms of security, it ensures data availability, integrity, as well as security by means of erasure coding, replication, data protection mechanisms like snapshots, and encryption. It provides end-to-end checksum, spectrum scale RAID, and NIST and FIPS certification along with file audit logging as well. With this, I end my presentation. Thank you.